So let's take a look at energy and reactions exercise number 2, where we're interpreting energy diagrams. And what I want you to recognize here is that the number one thing that you need to do right away is decide if this is exo or endothermic, because that is going to tell you a lot of things about that particular reaction. So remember that in an exothermic reaction, we're going to have the basic structure where the products end up at a lower energy. In an endothermic reaction, they're going to end up at a higher energy. Now, let's look at our first example here. You can see that our products are at a lower energy than our reactants. And so this example is exothermic. Because it's exothermic, there's several things that I know are true about the reactants in comparison to the products. So we can state this either way. Let's state it in terms of products. So our products are lower in energy. That means that they have stronger bonds, right? That's where that stability comes from. That means they're less reactive. Other things that you should realize, of course, is that the delta H is negative. One of the ways you can tell that is, again, you can look that we're moving down as we go from reactants to products. And so in this case, we're dealing with negative 392. The activation energy for the forward reaction is always easy to tell. It's just whatever you're given for the size of that hump. But remember that for the reverse direction, for an exothermic reaction, I'm going to have to add up these two numbers, right? Because I got to go up 392 to get to here, and then up another 19 to get over that particular hump. And so when I add up those two numbers, right, I get a total of 400 and 11. All right, so I can do all of that before I look at my choices. And I would encourage you to do this, right? It's always easier to kind of know what you know before you start looking at the choices. They can kind of throw you off. So let's look at our possibilities one by one. The first one says the magnitude of the activation energy for the forward reaction is larger than the magnitude for the reverse direction. That's never going to be true for an endothermic reaction, because in an endothermic reaction, the reverse direction is going to start from lower than the forward reaction started from, because again, our products are lower than our reactants. The sign of delta H is positive. That's not true. Again, we know if it's exothermic, that's a negative value. The value of the activation energy is negative 392. Again, that is the delta H value. Make sure you understand delta H is reactants minus products. Activation energy is transition state minus reactants. The magnitude for the reverse reactions activation energy is larger than 19. There we have a true scenario, right? That is true. We just said that it's 411. The energy of the products is lower than the energy of the reactants. That's true. Again, that's always the case for an exothermic reaction. And finally, it says the reactants are less stable than the products. Absolutely, right? Because again, the reactants are at a higher energy, which means they are less stable. So again, kind of thinking about those things before you look at your choices is going to make deciding if your choices are right or wrong much easier. Let's look down here at the bottom where we have an endothermic reaction. And so the things that we talked about at the top are going to be the opposite down here, right? Our products are at a higher energy. That's what makes it endothermic. We don't get as much energy out when we make our bonds that we put in to break them, because our products have weaker bonds, and again, that's weaker bonds in comparison to our reactants, and our products are going to be more reactive than our reactants. We're going to have a positive delta H. In this case, you can see, again, we're moving up from reactants to products, that it's 226. And in terms of activation energy, the activation energy of the forward direction, which is generally kind of understood, is going to be greater than the activation energy for the reverse direction, right? Because in the reverse direction, I'm already starting 226 kilojoules up that total 358. And so my activation energy to get over that hump is that 358 minus my 226. And so it's only 132 kilojoules to get over that hump. Now, with that said, let's look at our choices and decide which ones are true. The first one says that the magnitude of the activation energy for the reverse reaction is smaller than 358. That's true. Again, the reverse reaction is going to have a smaller activation energy. The value of delta H is 358. Nope, that's the activation energy, right? Remember we said that the delta H is positive 226. The energy of the products is lower than the reactants. Again, that's not true. We can see that the products are way up here compared to the reactants down here. Remember, these are reactants. These are products. The magnitude of the activation energy for the forward reaction is smaller than the magnitude for the reverse direction. Again, that's not true. We know it's 132 for the reverse direction, it's 358 for the forward direction. The delta H is positive. Again, that's true of every endothermic reaction. And the products have stronger bonds. Again, if the products are higher in energy, that means they have weaker bonds. They're not as stable. Strong bonds make something stable, lower in energy. All right, so that one's takes a little bit of effort to kind of think through what you know, read through the choices. And so take your time, make sure that you understand kind of each statement. If you have any questions, don't feel free to reach out to me by email.